Hello and welcome to our algebra lesson for today. Today we're moving into chapter 7. So we're going to be going over 7-1, which is going to be talking about zero and negative exponents. So we've seen patterns in exponents before. We've worked with exponents before, so we know sort of what exponents are and what they do. So let's go through a few real quick right here, right? 2 to the power of 1 is the same thing as saying 2, which equals 2. 2 to the power of 2 is the same thing as saying 2 times 2, which times 2 and would give us 8. Oops, 2 not 3. There we go. 8. So we see this pattern, right? I know what's going to happen. I know what these mean. So you can be happy about this. But oh, that's a smile, not a frown. Pretend like I smiled. But then there's a tough thing to kind of figure out. Does it mean if we go in the opposite direction? We see this pattern. So what does 2 to the power of 0 mean? Does it equal 2? What would it mean here? Are there 0 2s? Does it just mean it's a 2 to the power of nothing? This one, the pattern, we don't really know where the pattern goes from here, right? It's always been something that's a little confusing, and it still is confusing. So that's sort of what we're taking a look at today. So let's go ahead and take a look at our standard for today. And our standard for today, we have 2 of them. The first one is going to be n dot rn 0.1. n dot rn, there you go, n dot rn 0.1. And what this standard states is we are going to explain how the of rational exponents follows the properties of integer exponents to those values. Allowing for a notation for radicals in terms all right, and that is a complicated, long, weird standard. So I'm going to read it now that I've written it down. Explain how the definition of the meaning of rational exponents follows from extending the properties of integer exponents to those values, allowing for a notation for radicals in terms of rational exponents. So you're going to see how that we're talking here about the meaning of rational exponents follows patterns, basically, is what they're saying. It follows from extending properties of integer exponents, these patterns we're talking about. And our second standard is n dot Rn point 2. This one's a little shorter, and it states rewrite expressions involving radicals and rational exponents using the properties of exponents. Okay, so those are our two standards that we're going to be talking about today. As you can see, they're all about and the negative exponents today. There's a few rules we're going to follow with that make this pretty simple. So let's go ahead and get into our input. We do have some language of the discipline today. They're not exactly terms. They're things we want to remember. There's two of them. Okay, so we can say this is going to be language of the discipline, but also go ahead and put our detail flower there too, because these are details, but they are terms or they are phrases we're going to want to remember. The first one is 0 as an exponent. When you have 0 as an exponent, what does that mean? Now, the rule behind it non-zero number a to the power of 0 equals 1 every time. Okay? There's not much of an explanation there. It's just a rule, right? For every non-zero number a to the power, if a number is raised to the power of 0, it equals 1. So let's get a few examples. So if you have 4 to the power of 0, it equals 1. If you have negative 3 to the power of 0, it equals 1. 0.14 to the power of 0, it equals, you're right, 1. Doesn't matter what number it is as long as it is non-zero. If you raise any non-zero number to the power of 0, it equals 1. That's it. Okay, now, if you want to, because I know me, as far as I go, I'm curious about these things sometimes. So I understand that anytime I see that, I can just equal it as 1. But I kind of want to know why. Now, if this isn't really making sense, you just go by the fact that if it's raised to the power of 0, it's 1. But I always like to dive a little deeper and think, why? Why is this true? Okay? At a few of these rules that we've done over time. Okay? Now, I know in 7th grade, one of the things we learned was when we started talking about exponents, different ways of combining exponents. So if you divide two of the same bases that have exponents, you just subtract their exponents. So let me refresh your memory by writing what that means. So if we had something like 3 to the power of 2 divided by 3 to the power of 1, as saying 3 times 3 over 3, divided by 3 to the power of 1. And we know that when we do something like that, those get to cross off. Right? So again, if I wrote it, let's say 3 to the power of 3 divided by 3 to the power of 2, that would be the same thing as saying 3 times 3 times 3 over 3 times 3, meaning we could cross, and still be left with 3. Same thing as saying if it's 3 divided by 2, it would be 3 minus 2 meaning we have 3 to the power of 1, which is 3. Same thing here. Which would equal 3 to the power of 1, which we know is 3. So we know that rule, right? That's something we've learned before. So what if we had this with 2 of the same numbers, right? Let's say we had something to the power of 2 divided by 3. 2, which would be 3 to the power of 0. And we know that this would be the same thing as saying 3 times 3 over 3 times 3, meaning we cross, and are left with 1 over 1, which is 1, which means sense. Okay? Now, it's a little confusing, but at least there's a way to prove it. Okay, so let's go ahead and move on. So every time let's go ahead and get our next sort of language of the discipline, which is going to be what happens when we see a negative exponent. What that means is for every non-zero number a and integer n, this happens every single time. A to the power of negative n is the same thing as saying 1 over a to the n. That negative sign means that we simply put our power over 1, or sorry, under 1. So for example, let's go ahead and get a couple examples. Write that as 1/7 to the power of 3. Same thing if we had something like negative 5 to the power of negative 2, it would be the same thing as saying 1 over negative 5 to the power of positive. It's a way to remember it. All right, before we get into any modeling, there is a little note I want to. This is going to be part of our details. With okay, that's one thing. 0 can never be the base with 0 as the exponent. You can never see 0 to the power of 0. Also, 0 as a base with negative powers mean you would divide by 0, which we know is. So these two notes down here are letting us know that 0 can't really be used as a base with 0 as an exponent or with negative powers because it's undefined. If we have 0 to the power of 0, that equals undefined. If we have 0 and let's say to the power of negative 3, what that really means is 1 over 0 to the power of 3. And we know we can't do that, which would be undefined. You can't divide by 0. You can't have 0 as a base with 0 as a power. You can't have 0 as a base with a negative power. Those are undefined. Okay? All right. Go ahead and move to a new piece of paper. We're going to get some of our modeling done. There we go. All right. All right, so we just have a couple modeling questions we want to go over today. So let's start. Oops. Oh boy, cross that out. Let's start with simplifying fractions. All right. Number one, let's say we have a simple problem of 9 to the power of negative. In the equation we showed in the other, or the formula we showed in our definition, it's going to be 1 over 9 to the power of positive 2, which would give us 1 over 81. And that's our answer right there. Number 2, negative 3.6 to the power of 0. That simplifies, as with any number that is non-zero, to 1. Simple. So that's all we're going to do with simplifying fractions. You just need to know the definitions we put down of these two situations. Now, let's talk about something a little bit. Simplifying exponential expressions. And for number 3, now using some of those items we saw from above, 5a to the power of 3 negative 2. Okay, let's say that's our equation. How are we going to adjust this? How are we going to simplify this? Well, really the only thing we can simplify is right here. We're using variables, so we can't really simplify anything. The only thing we can do something to is that, meaning everything would be written the same. 5 times 1 over b squared equals, now we can put this on the top because this would all be, and we can say 5a to the power of 3 over b to the power of 2. And that would be our simplified exponential expression. All right, now let's take a look at something a little different, a little strange. What if we had something like this? 1 over the power, or 1 over x to the power of negative 5. Now, negative in the exponent. So what are we? Over x to the power of negative 5. It's the same thing as saying 1 divided. We know what to do. We would say 1 divided by 1 over x to the power of positive 5. And this would then equal 1 over 1, right? And it would be 1, if we're going to be changing this, we want to change that to multiplication, times, and we would do the inverse, x to the power of 5 over 1. And since we know this is 1 over 1, we would simply get x to the power of positive 5. A lot of changing things around, but all we're doing is the same properties over and over and over and simplifying all the. Okay, now that we've simplified fractions and we've simplified exponential expressions, let's go ahead and evaluate an exponential expression. For this one, we're going to see what is the value of to the power of 3 t to the power of negative 2 for s equals 2 and t equals negative 3. Okay, so we have all the pieces. Now we just need to solve. Now there are two ways to do this. You can either simplify first, or you can substitute first. It's really up to you which way you'd like to do it. So I'm going to go ahead and do both of them so you can see both. But it's just basically up to what you prefer. You'll get the same answer in the end. We were going to simplify first. Let's go ahead and simplify. We write out our initial expression, 3 which would become 3 to the power of 2. The 1 gets involved up here, and the t would then become our denominator, t to the power of positive 2. Now that we've simplified and we're able to do this, we simply plug in. So now we have 3 times 2 to the power of 3 over negative 3 to the power of 2. Is 8. And 8 times 3 is going to give us 24 over negative 3 to the power of 2. 3 times 3 is 9, and negative times negative is a positive. So it's going to be 9. 24 over 9. We can simplify. 9 goes into 24. We can do it over here to make sure we're right. 2 times 9, 18. Subtract. And that gives us 8. No. Oh, I'm completely wrong. That gives us 6. There we go. 2 and 6 over 9 is the same thing as 2 and 2 over 3. Okay, so when we simplify, and 2 over 3. Okay, now let's go over to where we substitute first and see if we do the same thing. First of all, we write out 3 to the power of 3, t power of negative 2. That will then equal, we substitute in, 3 times 2 to the power of 3 times negative 3 to the power of negative 2. All right, then we just go ahead and start to do our work this way. We have 3 times 2 to the power of 3 over, and now remember, we do this because we flip everything around. This would become 1 over negative 3 to the power of 2, meaning negative 3 to the power of positive 2. And then we just simplify, which would again give us 24 over 9, which would again give us 2 and 2 over 3. Whether or not you simplify or you substitute first, our answers will need to cover for today and what our guided independent practice is. For our guided practice today, we have our PP but we're also going to do number 39 through 45 odd. So make sure we get those two done. Then our independent practice is going 7-1 quiz. That's our work for today. Good luck, have fun, and I will see you next time.